So in this video we are going to talk about particle in a one-dimensional box. Particle in a one-dimensional box. Particle in a one-dimensional box. One-dimensional box. What is meant by particle in a one-dimensional box? Suppose we have a particle and that particle is allowed to move in the x direction. Okay, so we have a particle here and this particle is allowed to move in the x direction, and it cannot move all the distances along the x direction, but its movement is restricted. Means it can move from x is equal to 0 to x is equal to L. X is equal to 0 to x is equal to L. It means that it can make the movement to a maximum distance of L. Okay, so it can make to and fro motion, but the motion should be restricted within this region. And how the motion is restricted in this region, and that can be specified simply by saying that the potential energy of the system, is infinity once the particle crosses this boundary. Okay, the boundary at x is equal to 0 is a boundary marked by the potential energy which is equal to infinity, and the same is the case with the boundary at x is equal to L. Means this boundary, means the boundary at x is equal to L, there also put the potential energy is infinity. Okay, but inside the box the particle is not under the influence of any external force, or in other words we can say that within the box the particle's potential energy is 0. So this is a one-dimensional box. It is not like a box that we are generally dealing with. For example, we generally use the box of of some of some square side, or some various kinds of box, right? And rectangular box or whatever. So here it is not like that. Why we are calling this a box? Because we only wanted to say that this particle cannot escape from the region where it is confined to move. Box is also like that, right? If we are putting something inside the box, it is very difficult for that particle to go out of the box, because box will be already closed, and whatever object we are putting inside the box, that object has to sit somewhere inside the box, or the object has to lay somewhere inside the box. So that is why we are saying the analogy box here also. Here the particle is confined to move only from x is equal to 0 to x is equal to L, and nowhere else the particle can move. So that is why we call this as a one-dimensional box. Okay, so in this one-dimensional box the particle is confined to move. And now what we are going to do is we are going to quantum mechanically treat this one-dimensional box system. Okay, so we already know that the box dimension is from x is equal to 0 to x is equal to L, and the box is also characterized by some two boundaries at x is equal to 0 and x is equal to L, which is the boundary corresponding to infinite potential, and the particle can never cross this infinite potential barrier and go out of the box. Okay, so now let us constitute the Schrodinger wave equation for the system. Schrodinger wave equation for the system. So whenever we are dealing a system quantum mechanically, what we have to do is we have to set up the Schrodinger wave equation for the system. So Schrodinger wave equation is h cap psi is equal to E psi. You already know this. H cap psi is equal to E psi, where h cap is a Hamiltonian, right? So for every system there will be some particular Hamiltonian, and the Hamiltonian depends upon the state of the system, or the features of the system. Okay, so we can constitute the Hamiltonian for this particular system. H cap is equal to minus h square divided by 8 pi square m d square by dx square. Okay, we don't need to write d square by dx square plus d square by dy square plus d square by dz square, because y and z are 0 in this case, because the particle is moving only in the x direction. So we need to use only d square by dx square in this particular case. Okay, so that is the kinetic energy part of the Hamiltonian. And now we have to include the potential energy part. Potential energy is V, where inside the box the potential energy is 0. So again we can write like h cap in this case is equal to minus h square divided by 8 pi square m d square by dx square plus 0. Okay, so this is a Hamiltonian. Now with this Hamiltonian we are going to construct the Schrodinger wave equation for the system. So the Schrodinger wave equation is minus h square divided by 8 pi square m d square by dx square of psi, where psi is the wave function or state function of the particle in a one-dimensional box. We don't know what is the expression for psi at this moment. We just assume that psi is the wave function of this system, and we just give the psi in the Schrodinger wave equation. Okay, so d square psi by dx square, or that is h cap psi, is equal to E psi. Okay, E psi. So we can rearrange this equation further. That is d square psi by dx square is equal to minus 8 pi square m e divided by h square into psi, or I can write it like d square psi by dx square is equal to k square psi minus k square psi, where k square is equal to 8 pi square m e divided by h square. Okay, so let me write it again like d square psi by dx square plus k square psi is equal to 0. Now we have a standard second order differential equation, and the solution of this differential equation is psi is equal to, you already know the solution of this type of equation because we already learned the free particle in one dimension. There also we encountered with this type of a differential equation. So psi is equal to a sine kx plus b cos kx. Okay, psi is equal to a sine kx plus b cos kx. Okay, that is the general solution for the Schrodinger wave equation for the particle in the one-dimensional box. Okay, now this equation is very important for us, so let me keep that in a box. Okay, so k square is equal to 8 pi square me by h square. I will use this equation at a later stage. And now we have a psi is equal to a sin kx plus b cos kx also. This is also very important. Okay, so let us go further. Now what I am going to do is I am going to assume some conditions, okay, and because some boundary conditions, because I wanted to get the value of a and b. So let me assume that the particle is at the first boundary. Particle is at the first boundary, means particle is just meeting this first boundary. That is, the particle is at x is equal to 0. At x is equal to 0, you know that once it crosses x is equal to 0, this point, and that point corresponds to v is equal to infinity. Therefore, when the particle comes here, at that point, psi will be equal to 0, right? So, at x is equal to 0, at x is equal to 0, at x is equal to 0, that is the first boundary condition. At x is equal to 0, okay, and x is equal to 0, at that point psi will be equal to 0, because x is equal to 0 corresponds to infinite potential barrier, and the particle cannot cross that potential barrier. It means that the psi will become 0 at that point, or the particle cannot cross that point. So at x is equal to 0, psi is equal to 0. We are going to put this condition in our psi equation. So 0 is equal to a sine k into 0 plus b cos k into 0, right? Or in other words, we can write 0 is equal to a sine 0. Sine 0 is equal to 0. So we can neglect the first term, and what is remaining is b cos 0. That is b cos 0, or b cos 0 is equal to cos 0 is equal to 1. Therefore, b cos 0 is equal to b. So what we got from this one? From this condition, we got that b is equal to 0. The value of b is equal to 0. Okay. So this is important. B is equal to 0. So let me put that in the bracket. We from by applying one boundary condition that by applying one boundary condition that x is equal to 0, psi is equal to 0, we found that b is always 0. Okay, and now I'm going to apply the next boundary condition, that is at x is equal to L, that is the second boundary. Okay, at x is equal to L, there also the potential energy is infinity. Therefore, the wave function cannot exist here, or the particle cannot penetrate that point. So that is x is equal, psi is equal to 0 in that point also. Okay, so let us put this boundary condition here in our refined wave function. What is our refined wave function? Psi is equal to a sine kx. That is a refined wave function, because the next part will be equal to 0 because b is 0. So the refined wave function is psi is equal to a sine kx. So we are going to substitute the next boundary condition in this refined wave function, psi is equal to a sine kx. So psi at the second boundary is equal to 0 is equal to a sine k into L, or a sine kl is equal to a sine kl is equal to 0. Okay, so this is possible in two ways. A sine kl is equal to 0 is possible in two ways. The first possibility is that a is equal to 0. Okay, that is the first possibility. Okay, and the second possibility is that sine kl is also equal to 0. Okay, if either of this is true, then this equation will be valid. Okay, so either a is equal to 0 or sine kl is equal to 0. Which one is possible? Can you think what is possible? You suppose that it is a is equal to 0. You suppose that a is equal to 0. Then what will be the psi function? This is a psi function. Then psi is equal to 0 sine kx, that is psi is equal to 0. It means that for whatever value you are giving for x, means whatever value you are giving for x means at whichever position you are trying to observe the particle. X means it is from here to here, right? X is equal to 0 to x is equal to here. So whatever value you are trying to put for x, or at whichever position you are trying to watch the particle, okay, the psi will be 0. Psi will be 0 because psi is independent of x. For any value of x, psi will be 0 in this case, right? So that is impossible. The particle must be somewhere inside the box. So at some point x, the particle should be there. So this equation, what we are getting from here, psi is equal to 0 for any value of x is equal to 0. That is an impossible condition. So this is impossible. This is impossible. So a is equal to 0 is not a possible condition. Okay, that is not possible condition. So we have to go for the second condition, that is sine kl is equal to 0. Okay, so sine kl must be equal to 0. So if sine kl is equal to 0, you know that, then what are the possible values of for what possible values of theta? Sine becomes sine of theta becomes 0. Okay, sine theta is equal to 0 for theta is equal to 0, theta is equal to pi, theta is equal to 2 pi, then theta is equal to 3 pi, etc. For these values, sine theta is equal to 0. So it means that our KL must be 0, pi, 2 pi, 3 pi, etc. Or in other words, KL must be n pi, n pi. Okay. So if it is 0, then it is 0 pi. If it is pi, then it is 1 pi, 2 pi, 3 pi, etc. So KL must be n pi. Okay. So we can write it like KL is equal to n pi. From this equation, we can write KL is equal to n pi. At this moment, we may think like n is equal to 0, 1, 2, 3, etc. Because in these conditions, n is equal to 0 here, n is equal to 1 here, 2 here, 3 here, etc. So we may think we will tend to give the values of n as 0, 1, 2, 3, etc. But n is equal to 1, 2, 3, etc. only. 0 is not possible. I will tell you why 0 is not possible here. Okay. So you should not mistake that. Okay. Sin KL is equal to 0. So n pi in n pi n can also be 0 because that is true. If n is equal to 0, n pi will be sin n pi will be 0. That is right. But you cannot give n is equal to 0 in this particular case because I will tell you what's the reason. Okay. Now you know that KL is equal to n pi and since KL is equal to n pi, K is equal to K is equal to n pi divided by L. Okay, K is equal to n pi by L. So K is equal to n pi by L, and therefore we can write our refined wave function again becomes what was our first refined wave function? Psi is equal to A sin kx. And now we are going to substitute for k in this equation. Okay, then we will get the next refined equation, that is psi is equal to a sin k L, okay, A sin KL, where K is equal to n pi divided by L, n pi by L into what is remaining is x. Or we can write psi is equal to A sin n pi x by L, okay, psi is equal to A sin n pi x divided by L. Now you can give the possible values of n. Okay, if you give n is equal to 0 here, if n is equal to 0 here, okay, what's the consequence if n is equal to 0? If n is equal to 0, then psi is equal to A sin 0, that is equal to 0 always. Okay, means whatever value you are giving for x, that doesn't matter. For all values of x, psi will be equal to 0 if n is equal to 0. That is impossible, right? So psi must be the particle must be somewhere at any given at some given value of x. If you think that the particle is nowhere at the entire distance possible for entire values possible for x, or over the entire length of the box, as the particle is not there, then it is impossible. Particle cannot escape the box. Particle should be somewhere inside the box. Therefore this is not possible. Psi is equal to 0 over entire value of x is not a possible condition. That is why n is equal to 0 is not allowed. So n is equal to 0 is not allowed. Okay. Then what are the possible values of n? 1, 2, 3, etc. only. So when n is equal to 1, then the psi function become psi1 is equal to let me write it here. Then when n is equal to 1, then the possible value psi1 is equal to A sin pi x divided by L. Okay, that has some definite values between x is equal to 0 and x is equal to L. Okay, x is equal to 0 ആകുമ്പോഴും x is equal to L ആകും, s is equal to L ആവുന്ന കേസിലും എന്താകും, ഈ psi function 0 ആയി പോകും. പക്ഷേ അതിനിടയിൽ psi function definite values ഉണ്ട്. Therefore this is an acceptable wave function. When n is equal to 2, psi 2 is equal to A sin 2 pi x by L, right? 2 pi x divided by L. And when n is equal to 3, psi 3 is equal to A sin 3 pi x divided by L. Okay, these are all possible solutions of the Schrodinger wave equation. So now we have an expression for the wave function. The wave function's expression is a sine n pi x by l. So let me keep that within a box. Okay, let me keep that within the box because this is very important. We will use it further. So psi is equal to a sine n pi x by l. That is the solution of the Schrodinger wave equation. Okay, and now this solution is a very good solution, but still we don't know what is the value of a. അല്ലേ എയുടെ വാല്യൂ നമുക്ക് ഇപ്പോഴും അറിയില്ല. ഈ എയുടെ വാല്യൂ നമുക്ക് കണ്ടുപിടിക്കണമെന്നുണ്ടെങ്കിൽ we have to do the normalization condition. Okay, the normalization condition. Only by applying the normalization condition we will get the value of n. Okay, we will get the value of a. So let us do that also. Let us do the normalization. Okay, let's do the normalization. Okay, so when we do the normalization, it is possible that we can get the value of here. So what is psi? Psi is equal to a sine n pi x divided by l. Okay, that is psi. And let us do the normalization. Normalization means integral psi square dx from 0 to L. These are the possible values of x, right? This is the lower limit and this is the upper limit. So integral psi square dx is equal to 1. That is a normalization condition, right? So from this equation, we can find out the value of a, hopefully. Let us do this, okay? So integral 0 to L, psi is equal to a sine n pi x by L. So psi square is equal to a square sine square n pi x by L, n pi x divided by L dx is equal to 1. That's our equation. Okay, that means integral 0 to L. So let us take a square outside of the integral sign because that is a constant. So a square integral 0 to L sine square n pi x by L. Sine square n pi x by L. I am going to rewrite the sine square n pi x by L in another way because we know that sine square theta is equal to 1 minus cos 2 theta divided by 2. Okay, we can write it like this. So instead of sine square n pi x by L, I am going to write 1 minus cos 2n pi x by L, 2n pi x divided by L divided by 2. That 2 I can put it here, right? So a square by 2 integral 0 to L 1 minus cos 2n pi x by L dx is equal to 1. That's our new equation, right? So that is a square by 2 integral 0 to L 1 dx means integral 0 to L dx minus a square by 2 integral 0 to L cos 2n pi x divided by L dx, that is equal to 1. Okay, that means a square by 2 divided by 2 integral 0 to L dx, that is equal to x from 0 to L minus a square divided by 2 integral cos 2n pi x by L, that is equal to sine 2n pi x divided by L divided by 2n pi by L. Okay, sine 2n pi by L within the limit 0 to L, and that is equal to 1. Okay, that means a square by 2 x is equal to 0 to L means L minus 0. So we put upper limit minus lower limit, that is a square by 2 into L minus a square by 2 into sine 2n pi x by L divided by sine 2n pi x by L within the limit 0 to L. So first let us put L here. So we will get sine 2n pi because x is equal to L here, then L by L is equal to 1. So sine 2n pi divided by sine 2n pi by L minus sine. Now the lower limit is 0. So sine 0. Okay. So x is equal to 0, then it will be sine 0 divided by 2n pi divided by L. Okay, that is equal to 1. Or we can write like a square by 2 into L minus a square by 2 L minus a square by 2 into sine 2n pi. What is sine 2n pi? N is equal to 1, 2, 3, etc. Right? So sine 2n pi is an integral multiple of pi. Sine of any n pi or 2n pi is equal to 0. So in the integral multiples of pi, for all integral multiples of pi, sine of that will be 0. So this is equal to a 0. This is equal to this is equal to 0, and this is also sine 0 is also equal to 0. So both these terms will be 0. Okay, both these two terms will be 0. So this entire term is equal to 0. Okay, so we can write a square by 2 into L is equal to 1. Okay, that's what we can write. A square by 2 into L is equal to 1. From this one, we can write a square is equal to 2 divided by L, or a is equal to root of 2 by L. Okay, so a is equal to root of 2 by L. So now we have the value of a. So now we can substitute the value of a in our expression for psi. What is the expression for psi? Psi is equal to a sine n pi x by L. So our wave function psi becomes psi is equal to, now psi is equal to, therefore psi is equal to root of 2 by L sine n pi x divided by L. Okay, so this equation now, psi is equal to root of 2 by L sine n pi x by L is our complete wave function. Okay, we have everything here. So we know already, we know L, and if we substitute various values of L and various substitute of x here for different values of n, okay, then we will get the different values of psi at a different positions of x. Okay, so this is the complete wave function, that is root of 2 by L sine n pi x by L. So now you got how, just by starting with a no idea of wave function, right? We had no idea of wave function when we constituted when we constructed the Schrodinger wave equation first. At that time we didn't know what was psi, but by solving the Schrodinger wave equation, now we have obtained an expression for psi. Okay, this is called solving the Schrodinger wave equation. We will hear this: solve the Schrodinger equation, solve the Schrodinger equation, solve the Schrodinger equation many times. Whenever we are dealing with any system, you are going to hear this: solving the Schrodinger wave equation. This is the meaning of solving the Schrodinger wave equation. We construct the Schrodinger wave equation, then extract the value of the wave function. That is solving the Schrodinger wave equation. That is not enough. We have to now think about the energy also. Okay. So from the Schrodinger equation, the Schrodinger wave equation is h cap psi is equal to E psi. We have no idea of psi and E when we begin. Then we extract the values of psi and E by solving that equation. That is called solving the Schrodinger equation. Now we have the value of psi, and also we can get the value of E also. Okay. So now we have the wave function. That's fine. And with this information, now we are going for the energy. Okay, so let us think about energy now. Energy of the system. Energy of the system. So in order to get the energy of the system, I am going for an expression that I have already boxed here. Okay, we have k square is equal to 8 pi square me by h square. Okay, let me write that here. K square is equal to 8 pi square me by h square. So we have k square is equal to 8 pi square me divided by h square. Okay, and from this one, E is equal to k square h square divided by 8 pi square m. K square h square divided by 8 pi square. Now I am going to substitute for the value of k, because we have obtained the value of k as, see here we have obtained the value of k. Here is it. Okay, let me put that also in a box. K is equal to n pi by L. K is equal to n pi by L. So I am going to substitute this value of K in our energy equation, n pi by L. Since K is equal to n pi by L, E becomes n square h square divided by 8 pi square m L square, right? N square h square divided by 8 8. Okay, here we have a pi also, pi square, n square pi square divided by 8 n square h square pi square divided by 8 pi square m L square. Okay, I just substitute for k square. K square is equal to n square pi square divided by L square. Okay, so now what we have here is pi square and pi square are cancelled, right? Pi square cancelled from here. So what is remaining here is n square h square divided by 8 m L square. Okay, 8 m L square. So that is the energy of the system. See, the energy is equal to n square h square divided by 8 ml square. So let me put that in a box. That is very important for us. Energy of the system. Energy of the system is n square h square divided by 8 ml square. So now you can check this equation. Energy depends upon, okay, L. L is the length of the box. For a particular box, L is fixed. Okay, M is the mass, and for a particular particle, M is also fixed. And for a particular box and particular particle, M L square is a fixed value. H is a Planck's constant. So H square divided by M L square already is a constant. Okay, and that constant is multiplied by N square. But n can change. N can change, like n can be 1, n can be 2, 3, 4, etc. Any integer from 1, right? So for different values of n, we will get different values of E. Since the value of E depends upon n, let me call this as En. Okay, let me call this as En. En just represent that n, the E value depends upon n. Okay, so the energy values En can be calculated, or different possible energies of the system can be calculated. And this expression says that the first possible energy is for the least value of n. What is the least possible value of n? N is equal to 1. That is the least possible value of n. We already proved that, right? N is the least possible value of n. So for this least possible value of n, energy E1 is equal to h square divided by 8 m L square. That is the lowest possible energy. See, that is the lowest possible energy. Okay, and below that an energy is not possible. It means that this system, this particle in a one-dimensional box, can never reach an energy value which is equal to 0, right? It always has some positive value. H square divided by 8 ml square is a positive value, because Planck's constant is positive. Okay, L is a positive value, that is the length of the box. Mass is a positive value, so h square divided by 8 ml square is also a positive value. So this system always will have some energy greater than 0. Below that, an energy is not possible. What does it mean? Even if you are cooling this system to absolute 0, okay, even if you are cooling this system to absolute 0, you cannot minimize its energy below this. So this point, this energy is called a 0 point energy. Even if you are cooling the system to absolute and 0, at that point also, this system will have some positive energy. Okay, some positive value of energy. By saying positive energy, I don't mean the superstitious positive energy. ചില ആളുകൾ ഈ പോസിറ്റീവ് എനർജി നെഗറ്റീവ് എനർജി എന്നൊക്കെ പറഞ്ഞ് നടക്കുന്ന ആളുകളുണ്ട്. ഇതൊക്കെ ചെയ്യാമെങ്കിൽ പോസിറ്റീവ് എനർജി കിട്ടും, അതൊക്കെ നിങ്ങൾ ചെയ്ത് കഴിഞ്ഞാൽ നെഗറ്റീവ് എനർജി എന്നൊക്കെ പറയുന്ന ആ എനർജി എന്താണെന്ന് കൃത്യമായിട്ട് അറിയാൻ വയ്യാത്ത ആളുകൾ എനർജിയെ പറ്റി സംസാരിക്കുന്ന ഒരുപാട് കേട്ടിട്ടുണ്ട്. യൂട്യൂബിലും മറ്റുമൊക്കെ പലരും ഈ എനർജിയെ പറ്റി വാദോരാതെ സംസാരിച്ച് കാശ് തട്ടുന്നുണ്ട്. പോസിറ്റീവ് എനർജി, നെഗറ്റീവ് എനർജി, ആ അർത്ഥത്തിലല്ല ഞാനിവിടെ പോസിറ്റീവ് എനർജി പറഞ്ഞിട്ടുള്ളത്. ഓക്കെ, ഹിയർ വാട്ട് ഐ മെന്റ് ദാറ്റ് വി ഹാവ് some energy which is greater than 0. Okay, that is meant by positive energy. Okay. And now E1 is this E1 is a 0 point energy. 0 point energy. 0 point. So particle in a one-dimensional box, it has a 0 point energy. It means that whenever, even if that particle is cooled to absolute zero, that particle still have some energy, and this is a universal conclusion. Okay, whenever its particle is confined to move in a limited space, okay, whenever a particle is confined to move in a limited space, okay, then that particle will have some kind of energy like this, and its energy will be quantized also. So I am going to prove that energy will be quantized. So next I am going to go for n is equal to 2 case. Okay, n is equal to 2 state. So in that state, E2 is equal to n square h square divided by 8 ml square. That is 2 square means I have to take 4 h square divided by 8 ml square. Okay. And in the next case, n is equal to 3. E3 is equal to that is 3 square, that is 9 h square divided by 8 ml square. Okay. And when I am going for E4, okay, means n is equal to 4 state, E4 is equal to 16 h square divided by 8 ml square. So in all these cases, 8 ml square is the minimum energy. Okay, 8 ml square is the minimum energy. And the second one is second one is 4 h square divided by 8 ml square, right? Means 4 times the minimum energy. 4 times the minimum energy. And the next one is 9 times the minimum energy. 9 times the minimum energy. And the next one is 16 times the minimum energy. Okay, so we can write like that. So this is E1, and now this is equal to 4 for E1. Okay, this is equal to 9 E1, and this is equal to 16 E1. Okay, so this is how the energies are allowed. What does it mean? We have some fixed value of E1. Okay, so let that E1 be here. So let me write it here. These are the energies possible. So this is the box, the one-dimensional box. Okay, within the one-dimensional box, what are the possible values of energy? That is what I am going to write. Okay. So we have E1 here. This is E1. The energy E1 is here. This is E1. Okay. And the next possible value is E2. And E2 is 4 times E1. So let this be here. Okay, 4 times E2. E1. 4 times E1. 4 times 0. So if you are considering 0, then 0 is somewhere here. Okay, if you want to see 0, 0 is somewhere here, but that is not a possible energy value for this system. So this is the 0.0. This is a 0. But 0 is not possible for this system. So don't confuse that. This is also an allowed value. This is not an allowed energy value. But just to show you that what is height of E1. This is the height of E1. Okay. Okay. This is the height of E1. And E2 is here. E2 is here. This is E2. And what is the height of E2? The height of E2 is 4 times E1. So this is 4 times E1 from here to here. Whatever might be this is E1. This is 4 times E1. Okay, from here to here. So the difference between this one is 4 E1 minus E1. So this difference is 3 E1. 3 E1. Right? Okay, this is a difference. And when we are going for the next one is E3. E3 is 9 times E1. 9 times E1. So this is E1. So 9 times E1 is somewhere here. Okay, let me write it here. 9 times E1. Let me put it a little down. The scale may not be very nice. Okay. So still you may bear with that, because I don't have enough space to write all these things always. Okay, so that is why I write it here there. So 9 times E1. Let me put it here. 9 times E1 is equal to E3. So this is E3, and E3 is equal to 9 times E1. 9 times E1. This is 4 times E1. Okay, and 9 times even means from here to here, it is 9 times the distance of here to here. Okay, so what is the difference between E2 and E3? This is 4 E1 and this is 9 E1. So the difference between E2 and E3, this difference is 9 E1 minus 4 E1, that is equal to 5 E1. 5 E1. Okay, and if you are writing E4, E4 will be 16 times E1. E4 is 16 times E1. So E4 is somewhere here, 16 times E1. E4 is 16 times E1. Okay, so this is E4, and that is 16 times E1. And if you are taking the difference between E4 and E3, that is 16 E1 minus 9 E1, that is equal to 7 E1, right? 7 E1. 7 E1. So you can now look at the differences. The difference between first and the second is 3E1. Then the second and third is 5E1. Then next is 7E1, like that. The difference is increasing, right? So if we are going to higher states, the difference between the successive energy states are increasing. The difference between the successive energy states are increasing. That is very particular with this particle in a one-dimensional box. So if the particle is in the ground state, it will try to stay in this E1 state. This is a state. N is equal to 1 represents a state, and that state is represented by psi 1. Psi 1 is already written here. Psi 1. That state is represented by psi 1. What is psi 1? Root of 2 by L sine n pi sine pi x by L. That is equal to psi 1. Okay. So psi 1 corresponds to the energy E1, and after that the next state is E2, and that E2 corresponds to the wave function psi 2. Okay, so E1 corresponds to psi 1, and E2 corresponds to psi 2, and E3 corresponds to the wave function psi 3, and E4 corresponds to the wave function psi 4. നമ്മൾ ഒന്നാമത്തെ പോസ്റ്റുലേറ്റ് പഠിച്ചു അല്ലേ? For every system there is a wave function which represents the state of the system. അപ്പോൾ ഈ psi 1 എന്ന് പറയുന്നത് ആ സിസ്റ്റത്തിന്റെ സ്റ്റേറ്റിനെ റെപ്രസെന്റ് ചെയ്യുകയാണ്. ആ സിസ്റ്റത്തിന്റെ സ്റ്റേറ്റ് മാറാം, അപ്പോൾ ആ വേവ് ഫംഗ്ഷൻ എന്തായിട്ട് മാറും? psi 2 ആയിട്ട് മാറും. ഇനി നെക്സ്റ്റ് സ്റ്റേറ്റിലേക്ക് അത് പോയി കഴിഞ്ഞാൽ അത് psi 3 ആയിട്ട് മാറും ആ വേവ് ഫംഗ്ഷൻ. അത് അടുത്ത സ്റ്റേറ്റിലേക്ക് പോയി കഴിഞ്ഞാൽ psi 4 ആയിരിക്കും. അങ്ങനെ പല പല സ്റ്റേറ്റുകൾ പോസിബിൾ ആണ്. So for every state there will be some particular energy. So what do you want to understand from this one? So see, if the system is in the ground state, then system will try to occupy the E1 state, or the system will have the 0 point energy. If you are giving some energy to the system which is equivalent to 3E1, then the system will make a transfer, okay, or transition to the next higher energy level E2. അപ്പോൾ അതിന് അത്രയും എനർജി അബ്സോർബ് ചെയ്തുകൊണ്ട് അത് E2ലേക്ക് പോകാം. പക്ഷേ ഈ ഗ്രൗണ്ട് സ്റ്റേറ്റിലിരിക്കുന്ന ഈ സിസ്റ്റത്തിന് suppose you are giving only an energy which is equal to E1. Okay, the system is in the psi 1 state, and now you are giving an energy which is equal to E1, and that energy is not sufficient for that system to make a transition to the next higher state. അപ്പോൾ ആ E1 കിട്ടിയത് കൊണ്ട് അതിന് പ്രയോജനമൊന്നുമില്ല. It has to get to 3E1, then only it can absorb that energy and go to the next higher stage. Okay, it means that energy is quantized. It cannot absorb any value of energy. It can absorb only those amounts of energy which is sufficient for a transition from one allowed state to the next allowed state. That is why we say that this system is a quantized system. So energy is quantized. Okay, energy is quantized. Okay, so this is a quantized system, and this is a universal conclusion. Whenever a particle is confined to move within a limited space, whenever a particle is confined to move within a limited space, its energy will be quantized. It means that it cannot occupy in any energy value, in any energy value of its choice. It can exist only in certain restricted energy values. That is meant by quantized state. Okay, അപ്പോൾ നിങ്ങൾക്ക് മനസ്സിലായി കാണും എങ്ങനെയാണ് ഒരു പാർട്ടിക്കിളിനെ ഒരു റെസ്ട്രിക്റ്റഡ് സ്പേസിലേക്ക് കൺഫൈൻ ചെയ്യുമ്പോൾ ആ പാർട്ടിക്കിളിന്റെ എനർജി എങ്ങനെയാണ് ക്വാണ്ടൈസ്ഡ് ആകുന്നത് എന്ന് നിങ്ങൾക്ക് ഇപ്പോൾ മനസ്സിലായി കാണും അല്ലേ. So this is very important in quantum mechanics. When we are dealing with the chemical systems, so for example electrons, the electron will be confined to move only within certain limited space. Then it indicates that the energy of the electron is going to be quantized. Okay? For example, you are taking a bond, and the electron is confined to be within that bond. Okay, and there is some particular space in which the electron can occupy. It means that that electron can occupy only certain energy levels. If that energy is going further and further, sometimes that bond can be broken, or this type of situations we will see when we are dealing with the spectroscopy. Okay, so at this moment I wanted to tell that whenever a particle is confined to move within a limited space, then that particle will have quantized energy levels, or the energy of the particle will be restricted. Okay, now you already know that what is the energy difference between the successive states, and if you want to get a generalized formula, generalized equation for the energy of the successive states, we can do it like this. For example, now you can consider a transition of transition from psi n to psi n plus 1. Okay, psi n to psi n plus 1 means the state of at a particular time the state of the system is represented by the wave function psi n, and then that system gains some energy, and then it will make a transition to transition to the next higher state, which is represented by the wave function psi n plus 1. So psi n corresponds to En, and psi n plus 1 corresponds to En plus 1. So the energy transition is from En to En plus 1. Okay, so we have to supply energy for this transition, and now we are going to find out what is the energy that we have to supply for this transition from En to En plus 1, or what is the difference in energy between En plus 1 and En. That is what we are going to calculate. So delta E n to n plus 1. Okay, delta E n to n plus 1 is equal to E n plus 1 minus E n, the difference between E n plus 1 and E n. Okay, so that is equal to, what is E n plus 1? That is equal to energy depends upon n square h square divided by 8 ml square, right? N square h square divided by 8 ml square, or otherwise we can write n square E1. Energy of any state can be represented as n square E1. So let me write it as En plus 1 is equal to n plus 1 square E1, that is the energy of the n plus 1 the state, minus energy of the nth state is n square E1. So that is equal to n plus 1 the whole square, n square plus 1 plus 2n into E1. Okay, E1 minus n square E1. So that is equal to n square E1 minus n square E1. They will be cancelled. So what is remaining is E1 minus 2n plus 2en E1, or we can write like 2n plus 1 into E1, 2n plus 1 into E1. So that is the energy difference between the psi n plus 1 state and the psi n state. Okay, so delta E n to n plus 1 is equal to 2n plus 1 into E. So this is the energy we have to supply if we want to make a transition from psi n to psi n plus 1. Okay, so this is a generalized equation. Delta E n plus 1 n to n plus 1. So let me write it like delta E n to n to n plus 1. Okay, that is equal to 2n plus 1 E1. Okay, so this is a generalized equation, and if we expand this one, we can reach some other conclusions. So delta E is equal to delta E n to n plus 1 n to n plus 1, or we can generalize, we can write this symbol also. Means this symbol just means that the energy difference between these two. Okay, so delta E n plus 1 is equal to 2n plus 1 2n plus 1 E1, where E1 is equal to, what is E1? E1 is equal to, this is E1, h square divided by 8 ml square. Okay, so I am going to substitute for h square divided by 8 ml square here. H square divided by 8 ml square, that is equal to E1. So what is this equation saying? Okay, this equation says that for, if you are considering some values of L is the length of the box. If L is very large, if L is very large, if L is very large, for a large value of L, or for a very long box, okay, then the box is very large. Okay, so for a very long box, okay, in that case what will happen? As the length increases, the length of the box is in the denominator. As the length increases, delta E will decrease, right? Delta E will decrease. The energy difference will decrease. Means if you are stretching the box to a very high length, then the difference between the successive energy states will decrease. Delta E will decrease. So L and delta E are inversely proportional. Means when L is increased, delta E will decrease. Means that when the length of the box is stretched, then the difference between the successive states is decreased. It means that the quantization vanishes slowly. What is meant by quantization? Whenever there is restricted energy levels, we can say that the system is quantized. For example, you have energy state here, then another energy state here, one another one here, one another one here. This is quantized, right? If you have a system like this, here you have an energy state, and then next energy is here, the next one is here, the next one is here, and next one is here, and next one is here, and next one is here. Okay, I can write like this. Okay, if I take it all so much of the time, I can write like this. Okay, it means that there is no energy difference between the successive states. Means, what does it mean? It means that the system can sit anywhere in any energy level, or there is no restriction to the energy. That is what it is showing, or it is in a continuum, right? It means that if the energy is like this, this system can occupy, this system can acquire any value of energy. It can sit here, it can sit here, here, any value of energy, right? So there is no quantization. It means that if the difference in energy is decreased, or delta E is decreased, then the quantization vanishes. When the quantization will vanish completely, if you suppose that L is infinity, if L is equal to infinity, then then delta E is equal to 0, right? Delta E is 0 means quantization is completely vanished. The particle can occupy any energy. What is that? Do you remember? When we have already learned the free particle. In the free particle, there is no limit. It means that the length of the box is infinite, right? So when L is equal to infinity, it means that this system become a particle in the particle the particle is a free particle. Particle is a free particle in one dimension, and for a free particle in one dimension, there is no quantization of energy. We already saw this in the previous class. So this is the limit of the system. Okay, the particle, if the length of the box is increased to infinity, the particle in the one dimensional box will become equal to a free particle, and the quantization will completely diminish. Okay, that is one consequence of this one. And so if you want to get a better quantization, what you have to do, you have to keep L minimum. L വളരെ 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 കുറവാണെന്നുണ്ടെങ്കിൽ delta E വളരെ കൂടുതലായിരിക്കും. It means that the system can exist only in certain discrete energy level. The energy difference between the successive states is very high, means that the system has to get some particular amount of energy, then only it can move to the next higher energy level. Okay, so that is one consequence of this expression, or that is one thing that we can understand from this expression. Okay, and now we can think about m. What happens to delta I with respect to m? Okay, change in m. Okay, what happens to delta I with respect to m? So if m is very large, if m is very large, then what happens if m is very large? If m is very large, m is also in the denominator. If m is very large, then delta E will decrease. Delta E decrease means it approaches to the vanishing of quantization, right? Delta E കുറഞ്ഞു കുറഞ്ഞു വരുന്നു പറഞ്ഞാൽ quantization decrease ചെയ്ത് വരുന്നു. So if m is extremely large, okay, if m is extremely large means if m is some mass which we can consider in the macroscopic world, like the things that we are dealing every day, okay, like a ball bearing or a cricket ball or even a little stone. If m is very large, or for particles having large mass, then also the quantization diminishes. Okay, so this will not exist, this quantization will not exist if you are considering the particle in the macroscopic world. This quantization phenomena will exist only in the microscopic world. For example, the particles like electron, neutron, even atoms, molecules, etc. Okay, if the particle's mass is very small, then only this kind of quantization behavior will exist. Okay, so this is what we can understand from this equation. Okay, so now by assuming a hypothetical situation of a particle in a one-dimensional box, we have reached a certain very important understanding of what is happening in the microscopic world. We learned that in such particles will be quantized, and we also learned that when it comes to the macroscopic world, then the quantization vanishes. Okay, L is equal to very large എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ നമ്മൾ എന്താ കൺസിഡർ ചെയ്യുന്നത്, നമ്മുടെ സാധാരണ ജീവിതത്തിൽ നമ്മൾ കൺസിഡർ ചെയ്യുന്ന സെന്റിമീറ്റർ അല്ലെങ്കിൽ മില്ലിമീറ്റർ, ഇതൊക്കെയാണ് നമ്മൾ എല്ലായിട്ട് നമ്മൾ സാധാരണ മാക്രോസ്കോപ്പിക് വേൾഡിൽ നമ്മൾ കണക്കാക്കുന്നത്, അല്ലേ? ഒരു പാർട്ടിക്കിൾ 2 മില്ലിമീറ്റർ മൂവ് ചെയ്തു, അല്ലെങ്കിൽ 2 സെന്റിമീറ്റർ മൂവ് ചെയ്തു, അല്ലെങ്കിൽ 100 മീറ്റർ മൂവ് ചെയ്തു, 1 കിലോമീറ്റർ മൂവ് ചെയ്തു എന്നൊക്കെ നമ്മൾ പറയാറുണ്ട്. ദാറ്റ് ഈസ് the dimensions in the macroscopic world, and for all these dimensions the quantization will not exist. Okay, and also when we consider m is very large, means we are talking about the macroscopic particles like stones, cricket ball, footballs, or even at the large extents we can talk about the earth, moon, or whatever maybe. Okay, and so very large value of m, the quantization completely diminishes. Okay, that is what we are seeing. So this type of behavior exists only in the microscopic world, and when it comes to the macroscopic world, this type of behavior become insignificant. That is what we can learn from this one. Okay, I hope this was very interesting for you, and you learned well oh, about the behavior of particles in the microscopic world from this one. Okay, and we have to continue with this one, and I hope I will give more information about the wave function of the particle in a one-dimensional box, and the information about its wave nature and all these things in the next class. Okay, because this class is already going to be almost 1 hour. Okay, this is going to be almost 1 hour, so I wind up this one here, and in the next class we will see the part 2 of this topic, part 2 of particle in a one-dimensional box. Hope you enjoyed this lecture. If you have any doubt, don't hesitate to ask me, and as I always say, please keep your notebook with you, and please write it in your notebook. In that way only you can make these topics yours. Okay, in that way only you will become very much confident. Please do that. then you will be very much confident in writing the examination. Okay, so I wind up this lecture here. Hope you enjoyed this one, and thank you for watching, and stay tuned.